Let's develop the equilibrium constant Kc in a little more detail, and also talk in this video about Kp, an alternative form of the equilibrium constant that uses pressures instead of concentrations. This is a general point about the equilibrium constant that's worth keeping in mind. There are multiple ways to measure reaction progress or concentrations or what have you. We can even use something like partial pressures. Different values of K appear when we use different means of measuring reaction progress. Concentration and pressure are the two most common, and so those are the ones that we'll focus on here. So ideally, in the most general sense, what we'd like to be able to do is take a set of given initial conditions, a balanced chemical equation, and a Kc value, and write down the conditions at equilibrium. And by conditions here, what I really mean are the molarities or the concentrations of the reactants and products at equilibrium. Given a set of initial concentrations, can we write down equilibrium concentrations given these components? The first stage to that is writing down what we call the equilibrium expression for Kc, which is based on the chemical equation and the general rule that it's equal to product concentrations over reactant concentrations. So for example, for a general reaction, A molecules of A plus B molecules of B goes to C molecules of C and D molecules of D. Just by reading the balanced chemical equation, we can immediately write down that Kc is equal to products over reactants, right? So the concentration of product C raised to the power of little c times the molarity of product D raised to the power of little d, divided by the concentration of A raised to the A power times B's molarity raised to the B power. Just by reading the balanced chemical equation, we can write down an expression for Kc. And again, it's worth keeping in mind that this is a condition on the equilibrium state only, so all of these concentrations are concentrations at equilibrium. Remember to include those stoichiometric coefficients as exponents on each concentration when you do this. Now we're talking a lot about concentration in Kc, and referring to concentration makes it sound like we're either talking about reactants and products in solution and talking about something like more molarity, or we're talking about gases and thinking about the ratio of the number of moles of gas to the volume that that gas takes up. What about pure solids and liquids? Should those be included in equilibrium expressions? The answer is actually no. Pure solids and liquids do not ever appear in equilibrium expressions. To give us a sense of why this is the case, let's think about this ratio of, for example, the number of moles of a solid divided by the volume of a solid. And let's ask, does a chemical reaction actually change this value? The number of moles of a solid is proportional to the mass of the solid, right? The molecular weight is involved here. 1 over the molecular weight times the mass of the solid is equal to the number of moles of solid. Moles of solid divided by the volume of solid, well, that's just equal to the density. So this ratio of moles of solid to volume of solid is just equal to the density divided by the molecular weight. Density is a constant and it's intensive. It does not depend on the amount of substance present. The molecular weight is likewise constant and intensive. It's independent of the amount of material that's present. That's what I mean when I say that both of these values are constant as a reaction occurs. Essentially, as moles of solid are taken away, the volume of the solid decreases as well. That means that the ratio of the moles of a solid to the volume of a solid is a constant over the course of a reaction. Since it doesn't change, we leave it out of the equilibrium expression. An identical argument applies to pure liquids. The number of moles of liquid divided by the volume of a liquid is a constant equal to the density of the liquid divided by its molecular weight. The punchline is that pure solids and liquids do not ever appear in equilibrium expressions. Let's now talk about interpreting the value of K and consider a general reaction and its corresponding equilibrium expression. So this is the equilibrium expression that we derived before for this general equilibrium. A molecules of A plus B molecules of B goes to C molecules of C and D molecules of D. What does it mean for the value of Kc to be large, for the value of K to be much, much greater than 1? Well, that means that the product of the concentrations of C to the C power and D to the D power is much, much greater than the product of the concentrations of A to the A power and B to the B power at equilibrium. That means that the products C and D have much higher concentrations at equilibrium than the reactants A and B. We say that products are favored, since the concentrations of the products are much larger than the concentrations of the reactants at equilibrium. A small value of K indicates the exact opposite. A small value of K indicates that the concentrations of reactants are much larger than the concentrations of products at the equilibrium state. In this circumstance, we say that reactants are favored because they dominate the chemical system in the equilibrium state. A K near 1 implies that the concentrations of A, B, C, and D are all finely balanced, and that the reaction doesn't proceed to completion in one direction or another. In the equilibrium state, we have a somewhat balanced mixture of A, B, C, and D. As we alluded to at the beginning of the video, we can write the equilibrium constant in terms of any measure of reaction progress. For example, we can use partial pressures, and that leads to the equilibrium constant K sub P. For a gaseous species, the concentration, the number of moles of that species divided by its volume, is proportional to partial pressure. Just think about the ideal gas law. If we divide both sides of the ideal gas law by the volume of a gas, we get that its partial pressure, P sub I, is equal to the number of moles divided by the volume times RT. So, we can express the equilibrium constant for gaseous reactions in terms of partial pressures instead of concentrations, since as long as the temperature remains constant, partial pressure and concentration are just directly related by a constant of proportionality equal to RT. And it's still the case that writing, for example, an equilibrium expression in terms of product partial pressures divided by reactant partial pressures raised to their corresponding stoichiometric coefficients is still a constant. So we can write Kc in terms of partial pressures, but what we need to be careful to do is divide each pressure by RT, since molarity, N over V, is equal to the partial pressure divided by RT. When we do this, for example, for the dimerization of NO2 to form N2O4, we get R squared T squared in the denominator and only RT in the numerator, but we're dividing by RT in the numerator and dividing by RT squared in the denominator, so we end up with a factor of RT out front, the partial pressure of N2O4 divided by the partial pressure of NO2 squared. Notice that the squared survives, so the equilibrium expression, when written in terms of partial pressure, still has the same form as Kc. It just uses pressures instead of concentrations. So we can then take this chunk of this expression that has the partial pressures and looks a lot like the Kc expression and define it as Kp. We can write Kp as equal to the partial pressure of N2O4 at equilibrium divided by the partial pressure of NO2 squared at equilibrium. And just to emphasize that these are equilibrium concentrations, let's add an EQ subscript to both of these. Now, notice the relationship between Kc and Kp. There's a factor of RT that relates the two in this particular case. Each gaseous species brings along a factor of 1 over RT with it, because of this idea, again, that the partial pressure divided by RT is equal to the concentration. So when we relate Kp and Kc, we can say that Kp is equal to Kc times RT to the delta N, where delta N is the change in moles of gas that occurs in the reaction. In this particular case, delta N is equal to -1, since we're forming 1 mole of product gas from 2 moles of reactant gas. And if we plug in delta N is equal to -1 here and do some rearranging, we'll arrive essentially at the idea that RT to the first power times Kp is equal to Kc for the reaction of 2 NO2s forming 1 N2O4. So the general formula really is just based on the ideal gas law and the definition of K sub P as identical to K sub C except using partial pressures instead of concentrations. So Kp has the exact same form as Kc, it just uses partial pressures instead of concentrations. And in general, of course, the values, the actual numbers that Kp and Kc are equal to will be different. The only time these two will be identical is if delta N is equal to 0. That is, the reaction does not change the total number of moles of gas in going from reactants to products. Only if the numbers of gas molecules on both sides of the equation are equal will Kc and Kp be equal to one another. The factor of RT has some interesting implications. Because Kp is equal to Kc times RT to the delta N, if a reaction produces more gas, that is, if the moles of product gas are greater than the moles of reactant gas, then increasing the temperature is going to increase Kp relative to Kc. Increasing temperature exaggerates the difference between Kc and Kp. This should make sense because with more product gas molecules, those are going to exert a larger pressure at a higher temperature, increasing the value of Kp relative to Kc. Let's talk about the units of the equilibrium constant now. Kc appears to be a ratio of concentrations, indicating that its unit should be something like molarity, molarity squared, 1 over molarity, 1 over molarity squared, depending on the stoichiometric coefficients on the reactants and products and how many molecules of each we have. Kp similarly appears to be a ratio of pressures, indicating that we should have something like a pressure unit squared or to the -1 power or the -2 power or what have you, something like atmospheres, for example. However, for the purposes of our course, equilibrium constants do not have units, and we will not prove why this is the case here, but check out the optional video on proving the law of mass action to gain some insight into this. The basic idea is that what is actually appearing in the equilibrium expression are not molarities per se, but the relative value of a molarity relative to a standard. The standard happens to be 1 mole per liter, which is why we can simply leave off the units and not worry about it. And the standard for Kp happens to be 1 bar of pressure. And so again, as long as we're working in bars, we can just chop off the units. But because we're defining the K relative to that standard, we don't use units in Kc, Kp, or any other equilibrium constant. So to show you an example of this, an equilibrium constant calculated like this, 0.5 moles per liter times 0.2 moles per liter divided by 3.4 moles per liter, we might expect this to have overall units of moles per liter since these two cancel and we're left with moles per liter in the numerator. However, the way to really calculate this equilibrium expression is to divide each of those concentrations by the standard molarity of 1 mole per liter. This cancels out the units in each factor and leads to a dimensionless result overall.